A rocket launch is the most violent form of travel ever invented by humans. It is a 9-minute-long, continuous explosion that generates millions of pounds of thrust just to fight gravity. Yet, at the very top of this controlled detonation sits a small capsule with a human crew, aiming for a target the size of a football field, moving at over 17,000 miles per hour. The popular idea is that spaceflight is about daring and risk. But what if the real story is the opposite? What if the key to survival is not about embracing danger, but about controlling it with an almost obsessive discipline? This is the story of the Soyuz, a machine with 1960s roots that remains one of the most reliable spacecraft in history. It's not a documentary about a simple launch. It's about a system designed to survive the unsurvivable, where every procedure, every switch, and every line of code is a lesson written in the unforgiving language of physics and failure. The journey to orbit begins not with fire, but with silence and procedure, in the vast, windswept steppe of Kazakhstan. This is Baikonur, the world's first and largest spaceport. From here, the Soyuz rocket, a design with direct lineage to the 1950s, continues to fly. It looks almost archaic compared to its sleeker, modern counterparts. But this appearance is deceptive. Its longevity is not a sign of stagnation, but of a deeply ingrained philosophy of controlled risk. Here, every action is a ritual of engineering. The rocket is not assembled vertically in a massive building. Instead, it is pieced together horizontally in a hangar, where every component, every wire, and every bolt can be meticulously inspected. This is the first layer of control, a hands-on, deliberate process that prioritizes accessibility and verification over speed. Once certified, the entire rocket is laid on a specialized train car for a slow, almost ceremonial journey to the launch pad. This isn't just tradition, it's a physical manifestation of the system's methodical pace. At the pad, the rocket is slowly, carefully hoisted to its vertical launch position, a final, deliberate act of preparation before it can fight gravity. While the machine is being prepared, so are the humans. In the simulators at Star City near Moscow, the crew doesn't just train for a perfect 9-minute ascent. They train for the ascent to go wrong in 1,000 different ways. For hours, days, and months, they are subjected to every conceivable malfunction. Engine failures, cabin depressurization, guidance computer errors. The goal is not to learn a single flight plan, but to build an instinctive, procedural response to chaos. They are not training to be pilots in the traditional sense. They are training to be the final human component in a complex system of failure management. The real battle against the dangers of launch is fought and won here, on the ground, long before the countdown even begins. Finally, the day arrives. The crew suits up, each one sealed into their personal Sokol pressure suit. They complete the last of the pre-flight traditions, each step a familiar beat in a well-rehearsed rhythm. They ride the bus to the launch pad, ascend the gantry elevator, and are sealed inside the tiny Soyuz capsule. It's a cramped space, perched atop nearly 300 tons of kerosene and liquid oxygen. As the hatch is closed, they are alone with the sounds of the machine coming to life around them. The countdown is now audible inside the capsule. For the next 9 minutes, their survival depends on this controlled explosion remaining controlled. But the entire system, from the horizontal assembly to the endless simulations, is built around a far more terrifying and important question. What happens if it doesn't? The countdown reaches 0. It is not a liftoff, it is an earthquake. Deep inside the capsule, the crew feels the rocket come alive as a low, gut-wrenching rumble that builds into a continuous, violent roar. They are pushed back into their custom-molded seats by a force 3 to 4 times their own body weight. This is the brute force answer to gravity. For the first minute, the rocket accelerates straight up, a spear of fire against the sky. Then, it begins to pitch over, arcing toward the horizon. This is when it encounters the most dangerous point of its atmospheric flight, max Q, or maximum aerodynamic pressure. For a few seconds, the rocket is fighting not just gravity, but the very air it's flying through. The atmosphere, compressed at supersonic speeds, pushes back with immense force, threatening to buckle or tear the vehicle apart. The entire structure vibrates under the strain, and at the very top of this vehicle sits the ultimate insurance policy, the Launch Escape System. It's a small, powerful, solid-fuel rocket, armed and ready for one purpose: to save the crew if the main rocket fails. This system is not a theoretical safety feature. Its value was proven on September 26, 1983. Cosmonauts Vladimir Titov and Gennady Strekalov were strapped inside their Soyuz when, just over a minute before launch, a fire erupted on the pad. The automatic escape system failed to trigger. As flames engulfed the base of their rocket, two ground controllers in a distant bunker, with only seconds to act, manually sent the abort command. The escape rocket fired, ripping the capsule from the booster just 2 seconds before the entire vehicle exploded in a 300-ton fireball. The crew was slammed by an acceleration of 14 to 17 Gs, a crushing, violent force that briefly rendered them unable to breathe, but they survived, landing safely under their parachute 4 kilometers away. The system worked. In a normal flight, this explosive escape is never needed. Instead, at approximately 2 minutes, another critical event occurs. The 4 conical boosters that form the first stage, having spent their fuel, separate in a perfectly timed sequence. They peel away like petals, creating a pattern in the sky known as the Korolev Cross, a visual signature of the Soyuz. This is not just for show. It's a high-risk maneuver that must execute flawlessly to prevent a catastrophic collision. With the boosters gone and the rocket now climbing through the thinning upper atmosphere, the launch escape system has served its purpose. The risk of a low-altitude explosion or aerodynamic failure is largely past. In a quiet, decisive moment, it is jettisoned. The tower falls away, a silent acknowledgement that the battle against the atmosphere is won. But in doing so, the crew sheds its most powerful safety net. There is no longer an escape rocket to pull them from disaster. From this point on, their only way out is up. The rocket is now a wounded but determined machine, shedding parts of itself to gain speed. As the second stage burns through its fuel, it too becomes dead weight. With another precisely timed sequence of small explosions, it is discarded, falling back toward the atmosphere. For a brief moment, the third and final stage ignites, continuing the relentless push. Now, high above the dense atmosphere, the protective payload fairing that shielded the Soyuz capsule splits open and falls away. For the first time, the crew can see the raw, unfiltered blackness of space and the brilliant curve of the Earth below. The mission has fundamentally changed. The goal is no longer to go up, it's to go sideways, fast enough to fall around the planet without ever hitting it. This is the job of the third stage. Its burn is the most critical phase for achieving orbit. The engine pushes the vehicle horizontally, accelerating it along the edge of space. The crew is again pressed into their seats, but the stakes are now about precision, not just power. The engine must burn for a duration calculated to the fraction of a second. A few seconds too long, and they are thrown into an unplanned, higher orbit. A few seconds too short, and their arc will inevitably bend back toward Earth. Flight controllers on the ground watch their telemetry, knowing that this single burn determines the success of the entire launch. Then, at approximately 9 minutes after liftoff, the engine cuts off. The transition is instantaneous and absolute. The deafening roar and the crushing G-forces vanish, replaced by total silence and the surreal sensation of weightlessness. The dust and ice particles that were shaken loose inside the capsule begin to float gently in the air. This is it. This is orbital insertion. They are no longer riding a rocket. They are in orbit, but they are still attached to a dead rocket stage. A few moments later, a series of quiet, mechanical thumps signal the final separation. The Soyuz spacecraft is pushed gently away from the spent third stage. Then, with a series of soft whirs, it begins its transformation. The 2 solar arrays, folded like fans for launch, unfold and lock into place, turning to face the sun. Antennas for communication and rendezvous navigation deploy. The Soyuz is now a living, self-sufficient ship, generating its own power and communicating with mission control. It is a tiny, functioning outpost in the immense void. It is safely in orbit. But its destination, the International Space Station, is hundreds of kilometers away, a moving target also traveling at over 17,000 miles per hour. The violent ascent is over. Now, a cosmic chase is about to begin. Now in orbit, the task seems simple. Point the spacecraft at the station and fly over. But in the unforgiving vacuum of space, intuition is a dangerous guide. To catch up with a target in front of you, you cannot just hit the gas. In orbital mechanics, adding thrust raises your altitude, which moves you into a higher and therefore slower orbit. You would actually fall further behind. The real solution is a counterintuitive ballet of patience and precision. To reach the station, the Soyuz must first fire its engines to slow down, deliberately dropping into a lower, faster orbit that allows it to gain on its target from below. Over the next several hours, or depending on the mission, even a couple of days, the crew and flight controllers on the ground work in perfect sync. They execute a series of carefully timed engine firings known as phasing burns. Each burn is a calculated step in a cosmic chase, nudging the Soyuz's orbit, adjusting its shape and speed, and methodically closing the vast distance to the station. This is not a race. It is a slow, deliberate stalk, where every move is planned and verified. When the Soyuz is finally within range, the delicate final approach begins. This is largely managed by an automated rendezvous system called KERS. A set of antennas on the Soyuz and the International Space Station start a digital conversation, constantly exchanging data on their relative distance, velocity, and alignment. The Soyuz's flight computer processes this information, firing tiny thrusters in short, precise bursts to guide the capsule along a perfect trajectory toward the docking port. But automation is never blindly trusted. Inside the capsule, the commander's hands hover near the manual control sticks, their eyes tracking the approach on a screen. They are trained to take over instantly, to fly the final meters by hand if the automated system shows the slightest deviation. It is the final layer of redundancy. Trust the machine, but always have a trained human ready to save it. In the final few meters, the relative velocity slows to a crawl, just centimeters per second. The docking probe on the nose of the Soyuz extends, aiming for the cone-shaped drogue on the station's port. A slight bump, a quiet metallic contact. This is soft capture. Then, a series of powerful hooks and latches engage with a firm, final clank, pulling the two vehicles together to form a rigid, airtight seal. Hard dock is confirmed. Pressure is equalized. After a 9-minute launch and a multi-day chase, the hatch is ready to be opened. The crew has arrived. But looking back at this entire process, from the slow rollout in the step to this final, gentle connection, what have we actually witnessed? It is more than a successful flight. It is the execution of a philosophy. We have witnessed an entire journey, from the slow, deliberate rollout on the Kazakh steppe to the final, gentle contact with the space station. It is a process that begins with a controlled explosion and ends with a quiet, metallic click. But this success is not an accident, nor is it merely the product of a robust rocket. It is the physical manifestation of a deep engineering culture, one built around a single, guiding principle: control the risk. The legendary reliability of the Soyuz is not found in a single piece of hardware. It is found in the system's overlapping layers of defense. It's in the deep redundancy, where every critical system has a backup, and every automated process has a human one. The commander's hands hovering near the manual controls during docking is not a sign of distrust in the machine. It is the final, living failsafe. This culture is defined by its strict adherence to procedure, where every checklist and every rule is a lesson learned from a past failure, sometimes at great cost. It is a system that honors its history by refusing to forget its mistakes. This discipline is reinforced by relentless training, where crews spend more time practicing for things to go wrong than for them to go right. They are conditioned to see chaos not as a disaster, but as a problem with a procedural solution. And finally, it is a culture of evolutionary design. The Soyuz has been improved for decades, but it has never been replaced by something radically new and unproven. Each modification is a careful, incremental step, building upon a foundation of known performance. It prioritizes what works over what is fashionable. The true legacy of the Soyuz, then, is not its longevity or its iconic shape. It is a working blueprint for how humans can operate safely in an environment that is fundamentally hostile to life. The violent launch and the complex orbital chase are not gambles. They are a series of solved problems. Every step, from the Baikonur launchpad to the ISS docking port, is a testament to a philosophy that respects the immense danger of space and counters it with discipline, procedure, and redundancy. This is what turns a 9-minute explosion into a commute, and makes the extraordinary act of flying to space seem, against all odds, routine.